Equivalence of cardinality in musical analysis occurs extremely frequently. In order to develop musical texture, pitches are often repeated, either in the same voice or by a different instrument, so it is useful to be able to relate these sets based solely on their unique pitch content rather than looking at every single pitch attack. The cardinality equivalence relates sets whose subsets of unique elements are equal. It is important to remember that, as long as p-equivalence is not applied, all sets are ordered. Therefore, when dealing with the equivalence of cardinality of sets, the order of first instance of each element must remain the same, unless of course p-equivalence is applied. The model of this equivalence is much different than the previous models. Before, we relied on the fact that we had fixed dimensionality, which is based on the cardinality of sets, but with cardinality equivalence, we no longer have that luxury. We are now dealing with sets that have variable numbers of elements, and therefore models with variable numbers of dimensions. Ultimately, we would need to create a model with an infinite number of spaces embedded within each other, but realistically, we will only deal with a few of these levels. When building this model, it is easiest to start with the lower dimensions and build our way up. Because a set with only one element in it cannot contain repeated elements, we will start with sets containing exactly two elements. In a two-dimensional space, the set of points with repeated values, that is, x, y, where x equals y, lie along the line y equals x, for instance 1, 1. This point under C equivalence is mapped onto a single-dimensional space at the point 1. It no longer exists in two-dimensional space, but rather in one-dimensional space that is embedded within the two-dimensional space. In a three-dimensional space, there exists three embedded two-dimensional planes. Imagine a stack of two-dimensional planes. At the center of the stack is the zero plane, designated by the third element in the set, x, y, z, where z equals 0. If we assume that x also equals 0, and y can equal anything, that is, the y-axis, that line is part of the two-dimensional space embedded within the three-dimensional level of C space. Therefore, the first two-dimensional space relative to three dimensions is a plane x, y, z, where x equals z, and where y equals anything. The second is very similar, where y equals z, and x can equal anything. The last requires that y equal x, a line we are very familiar with, and z can equal anything. The intersection of these planes is where x equals y equals z, which is the single-dimensional space embedded within C space. Modeling four dimensions presents issues because the fourth dimension, that is time, is not a spatial dimension like the first three, but we can describe it as a three-dimensional space embedded within four dimensions. Because all of these models were limited to two dimensions, the line y equals x will be the only embedded subspace. In O space, this is the line that wrapped around the torus in both directions, and is the same in OP and OI space. In P space and I space, this is the boundary of the plane. Because T space mapped two dimensions onto a single dimension, the embedded subspace is the point 0, that is, the interval of a unison. OT and OPT spaces are circles similar to a clock, with the point 0 being the subspace. OTI and OPTI are similar to OT, but with a half circle. Despite the complexities of the infinite number of spaces embedded within each other, cardinal equivalence is an extremely valuable tool that lets us equate different musical textures and orchestrations rather than having to deal with repeated notes as a product of harmony. Ultimately, these models do not provide a practical tool for analysis. However, they provide an invaluable means for conceptualizing these complex spaces and the mathematics behind them. When looking at static node models, it is easy to forget that these spaces are actually composed of continuous pitches. Additionally, The use of video shows the motion between spaces, which would have never been possible to achieve in print. Modeling one space moving to another not only aids in the conceptualization of the spaces themselves, but provides deep insight into the way we analyze music and the implications of these relationships that are often assumed to exist without question.